Let's look at waves a little bit more using the visible spectrum. So here we have the visible spectrum from red to violet with their wavelengths written, and these are all in nanometers. So 750 nanometers would be red, 450 around there would be violet. So the wavelength goes down as the color moves towards blue. And we can see that down here. So our red wavelength is really, really long from here to here, compared to the wavelength for violet, which is really short, just between here and here. Well, which has higher energy? Well, for energy, we have to look at frequency. So which wave, the red wave or the violet wave, has a higher frequency? Well, if you think about if this wave was passing by, it would go up, down, up, down, up, down, up, down, up, down fairly quickly. Where if this wave was passing by, it would go up and down much more slowly. So the violet wave has a higher frequency, which means it has a higher energy. Remember that this fancy V, this nu, is frequency. If we look at the red wave has a low frequency, and therefore it has a low energy. So what we can say from this is that energy and frequency have a direct relationship. And what direct means, if one goes up, the other goes up. And if one went down, the other would go down. Now let's look at another relationship. Let's look at the relationship between wavelength and frequency. So we said that our violet wave, our high energy wave, has a high frequency. But if we look, it has a very short wavelength. If we look at the red wave, it has a very low frequency, but it has a long wavelength. So this tells us that wavelength and frequency have an inverse relationship. If one goes up, the other goes down. And we have equations to represent these relationships. For the energy and frequency relationship, the equation is energy, E, equals H, which is known as Planck's constant. It's a number that we'll look at a little bit later, times nu, the frequency. So the bigger that nu, the frequency is, the bigger the energy is going to be. And we have to, again, always pay attention for units. And in this case, the units for energy will be in joules, or J, and the unit for frequency will be in hertz. The unit for H is in joule times seconds. The other equation that we're actually going to use more is going to be the wavelength and frequency equation. This equation is C equals lambda, the wavelength, times nu, the frequency. So we have the speed of light, all waves travel at the speed of light, equals the wavelength times the frequency. The units for these are, the speed of light is always going to be in meters per second, Lambda, the wavelength, must be in meters. And nu, the frequency, must be in hertz. And the speed of light is going to be a constant. Constant means it's not going to change, and it's actually the fastest speed that anything can ever travel. So nothing can travel faster than the speed of light, and this number is always going to be the same. And the speed of light is the same for any electromagnetic wave. So radio waves, visible light, gamma rays, all of those different waves, even though they have different energies, travel at the exact same speed. And that speed is 3 times 10 to the 8th meters per second. So this number c, because it's a constant, is never going to change. It is always 3 times 10 to the 8th meters per second. And because we're talking about constants, I should probably give you what h is. H is known as Planck's constant. This is represented by the letter H, and it is equal to 6.636 times 10 to the negative 34th joule seconds.